Now let's illustrate how a power spectral density plot works using this example. So here we're going to be given this continuous signal defined here with this x of t. Notice here that the given signal consists of a cosine term with a frequency 5.6 radians per second, a sine term of 15.8 radians per second, a sine term at 26.3. So there's going to be, we actually know from the generating signal that it has 3 frequency components. And we're going to add a little bit of noise here. So what this eta value means is that I'm adding some Gaussian white noise that has a mean of 0 and a standard deviation of 3. Now, in reality, if we're doing a power spectral density analysis, we don't know what this x of t is. So in this example, I'm going to be generating data and then I'm going to analyze it. But when I analyze it, I'm going to pretend like I didn't know what the underlying generating function was. I'm going to act as though the data I created came off of a DAC box or an Arduino, and I'm going to do the analysis from there. However, since we actually at the end do know what generated the data, we're going to be able to do a comparison of what we analyzed and what we actually knew the function was that generated our data. But I'll say up front, generally we don't know the actual underlying function. So we have to trust what the analysis tells us about the signal. And then what we're going to look at is, since we can keep generating the data new, what we can do is we can take smaller time steps, and I can sample it for shorter or longer, and we're going to see what does that do to our power spectral density. What does that do to our spectral analysis if we play with the sample rate and the length of time at which we sample. So we can jump into MATLAB here. So the first thing I'm going to do is I'm going to create that generating function. So just take notice here that above 132, this is where I'm generating my function. This is not the analysis part. This is going to create my x values and my time values. After 132, I'm going to only use the x and the t values that were generated to do my analysis. So this is where I start pretending that I didn't know that underlying function. And what we're going to be able to do is modify some of the features in the generating and see how it affects our analysis. And this will be simulating if we were sampling faster or slower on our data acquisition system, or we were sampling for a longer time or a shorter time. We'll be able to do all of that when we generate the data. But once again, these lines 118 to 129 would probably, if we're analyzing real data, these would not exist. We would just have a string of x values and t values to start with. All right, so with that being said, 121, I'm establishing my function. So this was given to us. This is the function that we're trying to analyze. This is going to be the pure noiseless function at the moment. All right, so we see here we have the 6 times the cosine 5.6 radians per second times t, and then the sine term, and then the second sine term. So we have these 3 frequencies that we are adding together to get our signal. And then we will add noise in a minute. Now for this first kind of baseline version of this example, I'm going to sample this at 50 hertz, so 50 times a second. So notice here, I'm going to establish my time step, my dt, is 1 over 50. So 50 hertz, dt though is in seconds, so it's 1/50th of a second apart is every sample I have. My time step is going to determine my sampling frequency. All right, so my sampling frequency is going to be 2 pi over my time step. So in this first baseline example here, let me just run up to that section. I am going to be getting that my sampling frequency is 314 radians per second. Now, thinking back to your measurements and instrumentation course, the sampling frequency is going to determine also the highest frequency that we're going to be able to see in our power spectral density. And this is coming from that Nyquist criterion. And that is basically saying that we need to sample twice as fast as the highest frequency we want to be able to see. So I'm kind of arbitrarily picking here this 50 hertz sample rate. So if I sample it at 50 hertz, what I'm going to see is that I can only see signals up to 25 hertz. So this gets to what I was talking about before, that the sample rate determines the range of frequencies that are going to appear in the power spectral density. We're going to see then in 124 when I establish my timestamps. So I'm going to start at 1/50th of a second, and I'm going to go up to 10 seconds. And we're going to see that by modifying this, my length of time, that is going to change the resolution I have in my power spectral density. So how long I sample affects the resolution. How quickly I sample affects the range of frequencies in the power spectral density. All right, so we'll play with that a little bit later. Then in 125, I'm going to add just a little bit of noise to my signal. So this is where in 125, now that I've established the timestamps I'm going to use, 1/50th of a second apart up to 10 seconds, I'm going to put it into that inline function I made in 121, and then to every one of those, I'm going to add a little bit of this white noise, or this Gaussian normal distribution noise. So I was told in the slide that it should have a standard deviation of 3, and it should have a mean of 0. So that is what this is going to do. So let me just run this. And notice every time I run this, I keep running just this little bit here that's highlighted. In the command window, I'm getting different numbers each time. But each one of these is a random number drawn from a normal distribution with a mean of 0 and that standard deviation of 3. So I'm going to run just this little subsection so we can see what does the signal look like that we captured with our device. Right, so this would typically be the starting point because we wouldn't be generating the data in real life. We would just be given the set of data. So that's where we are at this point. Is these are all of the, capital X are all of the samples we collected. This is our actual signal, and little t, those are the timestamps of the signal. So the big X and the little t, these would be coming out of our Arduino. These would be coming out of our DAC box in real life. So this is where we actually will now start the spectral analysis. And it's going to look similar to what we just saw because the first step is going to be doing the discrete Fourier transform. Again, I'm going to be using kind of this manual method for now, where I'm using those definitions from the slides to get my A values and my B values. If we were actually doing this in application, we would probably use a better method like a DFT or a fast Fourier transform to do this, or we would go and use a more advanced PSD method like the P-Welch. But this is kind of the underlying mechanics of how those things work. They have more bells and whistles to them, but this is the very basics of what they're going to do is we need to, no matter what, find the coefficients of that discrete Fourier transform, that discrete Fourier series expansion. All right, so as before, I'm going to find the period, which is that capital T. And remember, this is based on all of the data that we collected. So we have a period of 10 seconds. The total time we sampled, 10 seconds. And then that fundamental frequency. Notice this is different than the sample frequency. The fundamental frequency is based on how long we sampled. Right? So W, and this is also going to be the resolution. This is going to be when we make our power spectral density, this is the spacing between the frequencies. So the longer we sample, the larger T is, the smaller this W or omega is, which means that the spacing between the frequencies gets smaller as capital T gets larger. And we'll see as we play with this how that works. And then our number of samples. So again, this looks very similar to that previous example, what I'm trying to do here. One difference though is the number of terms, the number of little n values I'm going to use. I'm going to take the maximum. And again, the maximum I can take is going to be based on how many samples I took in the first place. So that's what I'm doing in 139. I can take up to however many samples I have. Half that number is the number of terms I can use in my DFT. That's the number of A values and B values I can find is going to be based on half of how long I sampled, or the number of samples I took. So then I'm going to pre-allocate, and then we're going to see here that at this point this for loop is exactly the same as before. It's just I'm going to run it more times. My big N is larger because I want a lot more A values and a lot more B values. So let me run just to that point. Right, so running all of that, just so we can see what it looks like. I have a lot of these A coefficients. I have 250 since I took 500 samples, and I'll have 250 of the B values as well. And so we can see in the plot what this is going to look like. My capital W in my code is going to be the corresponding frequencies to each of these A values and B values. And this will be in radians per second. Okay, so let's see the W. So the largest frequency is going to be that 157.08. And notice that is half my sampling frequency. That's always going to be the case. I can only detect up to half of my sampling frequency on the plot I'm about to make. And then if we see the smallest value of this capital omega is going to be that 0.628, well, that is that fundamental frequency. And again, that's the spacing between any two neighboring frequencies. When we look at the plot, this is going to make a little bit more sense. Now what I want to do is I want to take my A and B values and I want to calculate the power. So again, by my definition of power for every term, so again, look at my A's and my B's, I want to take, like this would be the power on the highest frequency. I'm going to square this, and then I'm going to add it to this squared, and then take the square root, and that's how I'll calculate the power. So I'll have as many power calculations as I have terms. So I'll have 250 of these. Again, this will kind of all come together in a minute here when we look at the actual plot. What are we even looking at? So now I'm going to plot it. So notice for the power spectral density, what I'm looking at is the power compared to the frequency. So I'm going to, my independent variable is this W, that is all the corresponding frequencies in my analysis, versus the power, and this I do want in decibels. So I'm taking 20 times the 10 log of my power to make this plot. All right, so let's plot this, so we can at least see what we're talking about here. All right, so this is a very typical version of our power spectral density. So again, notice our x-axis is in radians per second. The minimum value is going to be that fundamental frequency. The largest value is half the sampling frequency. And this is in radians per second. Make sure you are careful with what units you're operating in, because sometimes you want this in hertz, because hertz is a little bit more of a intuitive unit, but this is in radians per second. So if we look at all the way over here, the highest x value, 157.1 radians per second, and the lowest is occurring at that fundamental frequency. That was based on how long we sampled. So what are we looking at in the y-axis? That is the power. That is the a squared plus the b squared. So the larger that coefficient was, the higher our power was. Well, between the cosine term, the cosine coefficient, and the sine coefficient. So it looks like a pretty jagged line here. There's some points it's low, some points it's high. But really what we want to notice from the power spectral density is look at these three clear peaks that we have on our power spectral density plot. Right? Everything else is relatively lower. Keep in mind this is a log scale, so these points are actually much larger than the points down here, but the log scale is going to let us kind of visualize this a little bit easier here. So there's three clear distinct points, and everything else is kind of down here far below those 3 points. All right, what does this tell us? This tells us that these three peaks, according to how we analyzed it, had the most power. The coefficients were the largest in front of the sine and or cosine terms at these three frequencies. So what we would say is that these three frequencies had the highest contribution, or these three frequencies were kind of the most powerful influencers in the signal that we analyzed. So where do they lie? Let's see. In decibels, we're not going to be worried about the y value right now. Let's look at the x value for right now. So the first peak, the x value, the frequency where the peak occurs, is at 5.66 about radians per second. The second peak, the x value, or the omega value, is 15.7 radians per second. And the third clear peak we see at about 26.4 radians per second. Right? And then everything else is pretty low in this case. All right, well, we have three peaks, but remember, we actually know what generated this signal that we just analyzed. So scrolling back up a little, remember from what was given to us, we knew that we had a signal or a cosine term at 5.6. Well, that 5.6 pretty well corresponds to that first peak we see. Then a sine term at 15.8, that's pretty close to this 15.7 peak. And then the third value, the 26.3, again very close to that third peak at 26.4. Now we do see these much smaller peaks and valleys happening down here. Well, this is going to happen because one, remember I added some white noise to the signal, so there's going to be some other kind of fluctuations, oscillations happening in this. And actually, let me go back to, this was the captured signal, looked like this. So by eye, we can't easily see that there's three main frequencies in the content of this signal. Again, additionally, we have from the noise some other little random fluctuations happening as well. So just looking at this original, now this is the signal versus time, the time series of it. Notice that here, this is the power versus the frequency. They're plotting, it's the same signal, but we're analyzing here the frequency content, and here we're completely in the time domain of it. So from just the time domain plot, nothing, at least by eye, is very obvious about the signals that make it up. Now we do have seemingly, if we do kind of peak-to-peak analysis, we can probably see there's definitely a pretty obvious repeating step between the peak-to-peak, and that might be able to tell us one of the frequencies that make up the content of our whole signal, but the power spectral density is giving us a lot more of that information. So the three peaks we see correspond to the three frequencies that we knew made up our signal. Now again, let's now pretend that we didn't know the underlying generating function, we just captured this data. We would still probably reach a similar conclusion, like, oh, okay, these three frequencies are going to be important. Now, why does this matter? It depends on the type of system we're looking at. Let's say we're looking at a biological system. So sometimes we could have like an accelerometer on a part of a body. Let's say it's the wrist of someone walking. Now, if someone's walking, they're on a treadmill, they're going to have a consistent pace, or even if they're walking over ground at a consistent pace, we would expect that as their arm swings, that's going to make a pretty regular repeating pattern. Now, we don't know the exact pattern it's making because it's not just going to be a simple pendulum or a simple double pendulum. There's a lot more going on in the system. But as you walk, your arm is going to swing. So something we'd be interested in is, what is the frequency of your arm swing? Because that's going to tell us something about how fast you're walking. However, if you have a condition like a tremor, your wrist is going to be oscillating not only due to your walking, but also due to the shaking from the tremor. So if we take the acceleration data off of the accelerometer we put on someone, we should expect multiple important frequencies that we might be able to detect. So a strong frequency we should expect at the pace at which someone's walking, and then we might see another peak at the frequency of the tremor that person has. If we have other, if we have a machine, a rotating machine, this can give us some insight into how that machine is operating. Let's say we have something that like an air conditioning unit that has a fan on it. Well, if we put an accelerometer on there and measure it for kind of an hour that we are running our AC unit, we should definitely expect to be able to see a high, strong frequency at how fast the fan is rotating. So if it's rotating at 1,000 RPM, we should be able to detect that from the accelerometer. However, the system is not only going to be oscillating or vibrating due to the fan rotating, but there's other things that are oscillating in our system. So we're going to see smaller pieces of content where those other pieces are vibrating. And this might be useful for diagnosing a problem with the AC system, that when it's in perfect working order, we should expect, for example, a very strong peak at the fan speed, and maybe there's 4 other peaks due to other things that are vibrating. But if we take this for an hour today, let's do it an hour tomorrow, an hour a year from now, we might see that where the location of those other peaks might be changing in time. And that could be indicative of a problem or an upcoming problem in our AC system. So this power spectral density, seeing the strength of individual frequencies, can be useful for, these two examples would be something like a health diagnosis. All right, so that's a little bit about why is this useful, but let's play with how we sampled this data. Now, we were able to detect these peaks, and here for the baseline, again, I just ran it, or I sampled it at 50 hertz, and I sampled it for 10 seconds. Let's say that we sample this slower, let's say at 25 hertz. What's going to happen? Well, what we should expect is, again, that we can only, the sample rate is going to affect the maximum frequency that we can see in our power spectral density. So if I lower it to 25 hertz sample, we can only see now, we should be able to only see up to 12.5 hertz. I'm going to sample it just as long though. Okay. And if we see the PSD that is created when we sample it slower, it is going up to only about 80 radians per second, which is, again, roughly that 12.5 hertz. Now, we still can see these distinct peaks here. That has not changed because, again, for this example, I sampled it just as long as the first time. So we still see those clear peaks. Now, in this example, sampling it slower didn't really matter because it turned out there was nothing interesting really happening even above the 25 hertz, faster than the 25 hertz. So even though it cut off everything from 25 to 50 hertz compared to the original, and nothing interesting was happening there. But let's sample this even slower, let's say 10 hertz. So this is going to be about, this is going to mean that we can only see up to 5 hertz. So again, here we can still see those 3 distinct peaks. Let me do it a little bit slower still, 6 hertz. And even slower. Now we're really losing some fidelity here. We're not getting much information. This is kind of extreme of pretty slow sampling if we go down that far. But okay, so like at 5 hertz, we can't really distinguish those peaks anymore because we're just sampling too slow, that the maximum is coming up way too fast. So we saw that the smaller, the slower we sampled, what it's doing is the range is being cut off of the maximum frequency that we can see. So let me go back to the original, that 50 hertz sampling. All right, so this is where we started. Right, those 3 distinct peaks are there. Now let's have what happens if we sample for a shorter amount of time. Well, again, the length of our sampling determines the resolution, the spacing between any 2 of these neighboring points. So what happens if I sample half as long for only 5 seconds? Still at 50 hertz, but only 5 seconds. Right, that's going to cut our resolution in half because we're going to see that that fundamental frequency is now twice as large. So the spacing between these points is now 1.23 radians per second. So with sampling half as long, we're still able to distinguish 3 of these peaks, but we're not going to get as close to the true value when we sample it. It's still not too bad. It's still going to be pretty close, about 5, 16.3, 26.4. Yeah, that's not too far off here. But what if I sample it even shorter amount of time for only 2 seconds? Again, this is going to make the resolution worse. And it's tougher to tell here. We're not able to, it looks still like we have 3 peaks, but if we didn't know that going in, we might not automatically say that. All right, they're actually still kind of close. Let's sample it even for less time. All right, now we've lost so much resolution, we really can't pick those peaks out to see what were the strong peaks in our original signal. Let's go back to 10. All right, let's go in the opposite direction. I can sample it for 20 seconds. Right, those peaks are still very distinct. We see that everything else is pretty low here. And I can keep going and sampling it for longer and longer. And we get really nice distinct peaks here. And we're not seeing any new peaks rising either. Let's go pretty extreme up to 100 hertz compared to at least our baseline. And again, we're seeing these 3 very distinct peaks. Everything else is very low here. So the longer I sample, all of these points are getting closer and closer together. And also because my resolution is increasing, these peaks should be getting closer and closer. They're already pretty close at 50 hertz for 10 seconds. Oops, sorry, I did this the wrong way. I want that to be 50. I want to sample this for 80. Now, the original sample rate, but sampling it for 80 seconds. So now I'm back to the baseline. So my maximum is still based on that 50 hertz sample rate. It's just my resolution is really, really good here. So again, if I pick out these peaks, because I have this even better resolution, I'm able to see what is the frequency where those peaks are occurring. And finally, let's actually look at the Y values here, the power at each of these. Right, so we have 14.14 for the first one. Let me just look at the first one. So that's the power at that 5.6 radians per second. Let's see what that 14.14 is telling us. So remember, the power is going to be the square, well, we're in decibels here, so that's 14.14 decibels at that frequency. Let me take that and take it back into the linear part. So what I'm going to need to do is, because I was taking 20 times the log 10 of my coefficients, I need to go in reverse. So that 14.14, I want 10 raised to the 14.4 over 20. And that is giving me a value of 5.2. Right? So if I go back here, that frequency of 5.6 about, I'm getting 5.2. So that's kind of close to the 6. Again, there's some noise here and there's some inaccuracies. What if I do it for the second one? So Y value 7.6. So that's what the plot gives me. 2.4, that's roughly close to that 2.5. And then the last signal at 21.31 gives me 11.62, roughly close to the 12. So the power I'm getting out of this is pretty close, with some margin of error, but pretty close, reconstructing not only where the strong frequencies were in my original signal, but relatively, or in this case actually absolutely, what their original coefficients were in front of the sines and cosines. Now this gets tricky if in my original signal I were to, at those frequencies, have both a cosine term and a sine term, because when I took the power, I was taking the square root of the sum of the A and the B term. But the power is not only telling us where strong frequencies are, but it's telling us the strength of the the cosine and sine term at those frequencies. So we have 3 strong frequencies, but actually the strongest one is at that 26.31 radians per second, slightly less at the 5.6, and slightly less than that at the 15.8 radians per second. And we see again that's reflected in that original signal.